Go.
All right. Thanks, Mike, for actually inviting me over here. I know that we have to do a little bit of rescheduling and such, but it's a great honor to be here. And yeah, especially with what all the different discussions that we've been having, it is really important that we kind of, from the PLM perspective, we take a step back and let's look at all the different aspects that are there. But when we are primarily talking about data, we have to think about, in some essence, the source of data. Is the data that we want to use AI, agentic, whatever we want to do with it, is the data itself?
You guys are going down, I got to go up.
Or is that something
Thanks
that
for the
we
presentation,
still are
guys. Are you coming back up?
having challenges with? And so that's what today's talk is going to be about, where we're going to be kind of talking about digital thread, right? But when we're talking about digital thread, it is talking all the way from the design all the way down to the production, basically. A little bit of background about myself. Before I started BQP, I was an aerospace engineer. I've done quite a lot of work in aerospace engineering firms, also in defense side, as well as on the civilian end, and all across the board. The thing that kind of really got me was the fact that the need for higher compute has always been there. We've always wanted more and more because of the fact that we want to, in some essence, digitalize everything that we're doing. We're of course seeing it from PLM side, but let's look at it from the high compute resource requirement that is needed is from the simulation end. And so then I actually was pursuing my graduate work in Minnesota, where I had the opportunity to work on extremely large scale simulations. And again, this was in the hypersonics regime. So I was working, or rather my project was funded by Office of Naval Research as well as AFSR. And over there, I had the opportunity of performing a use case that actually utilized about 200,000 CPU GPU cores.
Okay.
That I cannot that. Honestly, that's a number that is unimaginably large, especially if you're thinking from compute perspective, right? And even then, that was taking near a month for me to get their solutions back. And so again, the complexity of the simulation that I was running, and again, I'm not in the special when I'm doing this. There is a lot of workflow that is requiring huge amount of compute resources. And many times, unfortunately, engineers just end up have to basically make engineering decisions, put a lot of safety factors so that they can move forward, because of the fact that they cannot spend that much time, that much compute resources, just so that they are able to get a really good solution at the end of the day. They're better off doing quote unquote the experimentation side of it. And so that's what really inspired me and my co-founder to develop this startup, which again, the aim is to let's actually look at the computer utilization and look at how the solvers that we have currently, well, we've kind of figured out that they were not really meant for the compute that we have. So why not make solvers dedicated for the compute that we have right now, but also get ready for the future, which is of course quantum computing, especially from computation. If you're looking from the next generation computational workflow. And so that is where, when we're talking about digital thread, that is the computation is where we believe majority of the things kind of break down. Is, like I said, the data that we are talking about, is that good enough data itself? And of course, all of our vision is to have that seamless workflow from all the way to design to that end manufacturing process. How can we have that process done? And of course, a lot of the companies here who are working in PLM are trying to do that integration so that it's as seamless as possible. But let's also look at the initial part itself. And so that is where we believe that the whole area of this modeling and simulation, engineering simulation, again, it's derived from mathematical physics-based equations. So again, they are not necessarily like ML-based. Well, not contemporary ones are. The past ones are more rigorously ingrained with that the physics that is involved within it. And so the thing is that because of the high demands from the computational, the next logical thing is to start looking at, okay, how can we resolve the computational usage? And when we are looking at it from that perspective, currently 20% of GPUs, only I should say 20% of the GPUs are being utilized. So suppose you have, let's say A100 from NVIDIA, or let's say MI300 from AMD. When you're putting a workflow which utilizes that, of that 100% utilization, only 20% of it is being utilized. The rest 80% of the, again, from GPU architecture, there are threads, 80% of them are stagnant. Now, why is that? It is because of the fact that a lot of these solvers are high memory required. So because of that, there's only so much computing that you can do on GPU, because GPU is not a high memory architecture. CPUs are. And that's why there's a lot of communication that happens between CPUs and GPUs. And because of that, we cannot actually extract all the computing that is required. And so what's the next solution? Just get a heck load of more GPUs. We are seeing that trend right now with the huge amount of big data centers, as well as a lot of data centers that are coming out. But this is something on the software, on the solver side, is something that people have not really looked into. And actually, just recently, Jensen Huang from NVIDIA was on a podcast at Lex Friedman. And over there, he was talking specifically about this, because of the fact that, I mean, from them, of course, it's great that they are selling more GPUs, but they also understand that you're not using your GPUs correctly. So they want to upskill their users, their customers on that end as well. And again, this number is actually very widely quoted. I believe similar number was quoted yesterday by Andy as well. So this is becoming more and more of a knowledge. And now, if we have solvers that is utilizing that GPU space very perfectly, to be honest, now you don't need to add more infrastructure on top of what you have in order to satisfy what you want to do, but also the things that you wanted to do, but you were restricted because of the computing. And so that's what these solvers that we are working on are really kind of utilizing. Now, they are quantum solvers, and I'll get to that in a second. But there is a way where we can actually turn a quantum solver without needing an actual quantum computer to execute them. So there is a way, and I'll go into that, but the implications are huge because of this. Now, I'll go a little bit more into the problem itself before I get into that solution slide. But in essence, this is what we are talking about, and why the huge amount of resources and the computing time is required is because of the fact that we're actively trying to emulate the physical process, because simulations are simulating what would happen in reality. And of course, the more and more close we are getting to reality, that's where the high compute cost is really incurring or coming from. And so that is where the classical solvers, these incumbents that have these classical solvers already embedded in them, unfortunately, a lot of them have been developed over decades. And as we know, GPU, from that perspective, GPU is still a quote-unquote a contemporary compute and new architecture. And so right now the trend is, okay, we have these solvers which are working on CPUs, let's port them onto GPUs. I've done that work. It's really not, that's where this 20% really is coming from, is because of the fact that these are high memory usage solvers, and they're just porting it. Porting it just means that let's just put it on GPUs and let's just make it work. That's what they're doing. They're getting some form of speed up, of course, because of GPUs, but that's only like 2 times, 3 times. GPU has the promise of 10 times or more. And so that's where the big difference really can come into play. And so this is where we believe that quantum is the best answer. I know there are other answers as well. There are folks who are working on native GPU-based solvers and such. They've been doing it for years, and now, with that, now they're going into commercial land. But now, the thing is that GPU is not the end in terms of compute. We have to look at the next stage as well, because it took us at least a decade, because the first GPU paper on scientific compute came out back in 2009. We're in 2026. Well, what is that, 17 years later or so? we just recently were able to adopt everything to GPUs. Quantum is literally around the corner. It is less than 2 years away. Again, this is not just from, there's a lot of hype in quantum. I'm not just trying to add more hype to it. And that's why I don't say it's here today, which is what a lot of people say. For us to utilize our solvers on quantum hardware, we're predicting that it will take about 2 years, around 2028, or actually 2029, 2030, is the timeframe that we're looking at, where it will be possible for us to do it. So when quantum comes, what happens to these GPU-based solvers that are there? Quantum, you cannot put your GPU stuff on quantum, or even CPU stuff on quantum, because the solvers themselves are natively, or even the thought process of the solvers are different. And that's where I won't go too much into the quantum physics side of things, but you guys, may have heard some of these things, as I think majority of us are engineers, so you guys may have heard it in some physics course throughout your career about quantum superposition or entanglement and things along those lines. Those are basically very special, unique, and kind of hard to grasp concepts of quantum. But what quantum solvers are really doing is utilizing that inside it, embedded into it. And then when you have quantum computers, you can run it. Or if you want to run it on GPUs, you, again, simulate or emulate that process via tensors and tensors operations, and you're able to execute it. And so that's actually perfect because of the fact that, as many of you may know, that tensor operations are really well executed on GPUs. This is when we're talking about quantum inspired, which again means that you can run quantum algorithms or solvers without on classical CPUs and GPUs. All of them are essentially tensor operations. So you can run them very efficiently on GPUs, and that's where the earlier number that I was talking about is where it's really coming from. And so from one of the use cases or one of the areas that we have looked into is in optimization. We've already been able to give quite a few of our customers have already seen the advantages. And I'll talk about a couple of the examples in the use cases slide later on. But with optimization, there's a huge potential of what them realizing that they're leaving a lot of things on the table because of the fact that the traditional optimization is not able to get to the best solution, but also it's taking a huge amount of time. So reducing the time, but also helping them get a more efficient product at the end of the day. So that is where the whole aspect of going from that 20% to nearly 100% of that bandwidth or utilization. And actually, we work quite closely with the aerospace defense, but also semiconductor industry as well, the EDA from the simulation side. But talking to the end, basically the chip designers, what they realize, basically their customers, which are NVIDIA, AMD, and others. So those guys have told that they need to figure out this whole area of memory, and that's why even let's say Micron or some of the other players, TSMC and others, are designing chips which are increasing the memory or developing other products which can efficiently connect from GPU to CPU. And there are whole field within the HBM or high bandwidth memory. That's what I'm saying for. So yeah, and so that's what we are trying to do is that, of course, while they're doing all this, why not just make solvers that are more innately utilizing the resources that we have currently, instead of saying whatever we have, that'll be only used for 5 years, and after 5 years, it'll become redundant. Instead of just talking about it from that perspective, why not make it so that along the way, there is no external redundancy. And so one of the other places where we are doing a lot of work in is this physics AI. We talked a little bit about that yesterday. We heard about it from Andy yesterday. And what we are really trying to do is how can we incorporate, again, same thought process, incorporation of quantum technologies into the whole area of physics-based AI, or if you're looking for physics-inspired or physics-integrated machine learning field as well. And so there is a lot of potential for it. From that, there's of course a lot of development with regards to like surrogate models and things along those lines. Some of our work also has done this. So, for example, one of our use cases was with Space Force. I mean, it's not really was, it is with Space Force and a couple of other companies. And what we were actually able to do was one of the workflows that they had required an almost archaic solver, which took huge amount of time because it was actually an analytical solver. What we were able to do was use an AI-based tool, again a quantum-based AI tool, that we developed, so that we are able to again get the execution down very fast. But one unique thing what we saw, again talk about the memory utilization and such game, we're able to actually put that model on an edge device. And with that, there's a potential of putting it and deploying it in space. So now, instead of them collecting data in space, sending the data down to ground station, them doing the compute on ground, sending whatever the next steps are in terms of their entire process, sending the instruction back up, why not try to make everything to be on edge, right? And so with this specific use case, we've enabled it because of the fact that we've made it lots faster, but now this model is compressed down to 1 megabyte. So literally put it on, Jetson Nano or some other chips. We have done that and it works perfectly fine on ground. Now we're looking at how we can, like I said, deploy it in space and actually do basically real life testing on this. Again, that's one specific use case. We have done several of these use cases, and similar results are kind of beginning to show on that end as well. The other aerospace applications, again, talking about from optimization perspective, I think I was talking with John earlier about specifically some of these companies wants to look at from end to end, how can they optimize the entire workflow, but specifically the components that they're developing in-house to be ultimately cheaper, right? You're cutting down basically reducing the bottom line itself. So from that perspective, one of the use cases that we did with a large tier 1 aerospace aircraft manufacturer, was we were able to showcase the fact that with our design, using our solver, we were able to do 6% lighter design while still maintaining all the structural integrity that they care about, just by using our solver. We basically, how we started was that we utilized what we, after conversation, we utilized basically the things that they were using compared with what solution that we were able to get, and that's where we kind of got that. And from that engagement has actually proceeded quite well as well. A couple other ones are there with regards to on the simulation side. That's an active work that we're also doing. But that's where this connection, I'm not going to try to do the laser pointer, but that's where the connection to the digital thread really becomes important. Is again, that data generation that we have, why not have the data to be highly accurate? And the main reason for that not to be there, again, is because it's high compute intensive resource is required to do so. Another area, like I was saying earlier, we're beginning to do a lot of work with the semiconductor industry as well. So these are a couple of the other use cases where there is an application for it. And again, these are use cases from specific industries, but as you guys kind of know as well, it is really agnostic to the use case and agnostic to the specific industry. This is basically, we can go horizontal, we can go vertical, we got different verticals as well, and our product really does not have to change. If what may happen is we may have to integrate into the workflow, and that's something that we have done very recently with MATLAB from MathWorks. We now, because of that integration we have done with them, within MATLAB environment from anywhere, you can actually call our product, optimization product, directly and then basically use it. We've done the same with Python, Julia, basically going after those integration so that from the end user, of course, the infrastructure we really are saying from hardware you don't have to change, but even on the software stack, if you're able to integrate seamlessly within your workflow, the end user, only thing that they will experience is the result, the fact that they're able to get better results and faster results. They may not be even be aware of the fact that what is happening on the back end or how you got there. And so that's to the level of seamless integration that we have worked quite hard, and we will be continuously working hard on as well. And so this is where this is my last slide as well, how we really see things moving forward is that the ultimate goal is to make sure all the compute resources that we have on hand to use it as efficiently as possible. And even, I'm not just talking about now, but even years down the road, let's make sure of that, right? And we cannot be, as much as I love the industry, one thing I hate about our, the simulation industry is that we move slow. The incumbents that we have, they have a lot of the various products and such, so I can understand, but the movement is quite slow. And so there's always an afterthought. Like I was giving you the example of GPUs, I really don't want to see that to be the example of QPUs or quantum computers as well. And that's why the end goal, we have to keep that in mind. So that then when we look at it from that perspective, let's set up these milestones along the way. And that's what we really are kind of trying to do with a lot of our customers is essentially get them quantum ready. When quantum comes, you should be ready to go. It should not be that, okay, quantum is here. Now let's look at what can we do with quantum. Because if you're doing that, you're already losing out against your competitors. From industry level to even, to be honest, on like a international level, on a country by country level as well. I'm sure you guys have heard about a huge amount of investment that is happening across the board. This is why, is because we really don't want to be caught off guard. And then once quantum computers, it is really going to be that huge inflection, that iPhone moment that we like to call it. So that's my time. You guys can reach out to me. I think that's my LinkedIn QR code as well, and I've put some of my details up there as well. Thank you.
Thank you, Ruth. One of my first podcasts actually was with Quantiant, who's a Finnish quantum computing company. Maybe that's a funny fact, but one of the leaders in quantum computing is Finland because it's almost absolute zero almost all the year, and you have. That's the hard thing about quantum computing is it's got to be close to zero, and that's one of the interesting things I learned from him is that AI is actually helping quantum computing by eliminating the noise, because any noise basically ruins the calculation, and you need to keep as close to absolute zero as long as possible to calculate. As soon as you get any noise, boom, you have to stop abruptly. And so they're using AI to eliminate the noise.
Yeah, no, for sure. And why I say that quantum is a couple of years down the road, that's not to say that quantum computers are not ready right now. There are number of suppliers.
10 to 20 qubit ones.
Yeah, exactly. So there are quantum computers or 100 quantum computers where you can right now use them. But the thing is, because of the fact that they're very small or they're noisy and those types of things, they're unfortunately not at that industry scale relevant yet. That inflection is going to come within about 2 years, like I said. So when that happens, we should be able to run these quantum level, huge industry scale problems and that's where, like Mike was saying, AI is helping on the quantum technologies as well, but along the way, quantum, we truly believe is going to be that game-changing technology on compute side at least.
Very cool. Thank you very much. Great job. Actually, does the TPUs of Google, does that have any? Because which beat the GPUs in a benchmark about 6 months ago.
Yeah. So apart from the what is it, like the most popular processing units, TPUs are now becoming more and more prevalent. I mean, they have been over the years, and Google has been pushing the boundaries on that. But now, yes, TPUs are also going to be another, as part of the tech stack. How we see it is that CPU, GPU, TPUs, and QPUs, or quantum processing unit, all within the same data center. Basically, you're not going to have distributed data center or distributed framework. So, yeah.
Thank you, Ruth. And we do have a question.
Yeah, one question. So NVIDIA's about to release their system on a chip for consumer usage. So it's a GPU, CPU, and memory all together. Does that help bridge the gap, or are the problems you're trying to solve just like so big that a consumer grade computer just doesn't matter?
It's a step in the right direction, I would say. But ultimately, right now, I mean, data centers with comprising of CPUs and GPUs, what they're doing is there's that constant communication that is happening between the two. with this chip, that's happening as well. But now it's just kind of brought down into a singular chip. But that internal communication by NVLink or whatever is going to be happening regardless, right? And so what happens is that what we call overhead costs, basically the communication time that happens, when you go to an extremely large scale, those actually start mattering a lot as well. So yes, like I said, it's a step in the right direction, but we have to figure, like on the hardware side, we have to figure out to make memory-based GPUs. But let's not put everything on hardware. Let's look at it from solver and the software space as well. Right. Thank
Awesome
you.
job. Thank you, Root. Oh,
Mike, you mind if I just add a quick note?
absolutely.
So I noticed we have quite a few companies in the simulation space with various things. Just to give credit, right? We happen to be sitting on
Turns
top
it,
of the
any of them will turn the screen back on. That just blacks it out. And that turns it back to not slideshow mode. So it's already in slideshow mode.
Is there were two people attending.
But that goes to say, not just
One is
blacks.
Jim Cashman, for 20 years the CEO of ANSYS.
He was in here about 2 hours ago,
Okay,
right?
great. So Jim is downstairs.
Walter.
ANSYS. No, he's
ANSYS.
the CEO.
Oh, Jim, got it.
Jim Cashman, so CEO of ANSYS, he's on the board of Eris, but he's here.
And super nice guy,
Right?
fantastic
Super
guy.
The other guy that you should get hunt and kill, go find, is Gartner guy, Mark Halpern.
Mark Halpern.
Mark Halpern
Yeah.
has a PhD in CAE, right? He's been in the industry a long, long time. But if you want to amplify your story, right? This is how Eris got started. We convinced Gartner that we're doing something cool, even when we were a tiny little company. And then when customers call Gartner and say, "Listen, we're stuck. I can't simulate with ANSYS anymore. What's coming next?" Mark says, "Go talk to."
BQP,
there's
Cognizant,
some
and no
talent
space.
downstairs that's really worth networking. That was my point. Thank you.
Awesome. Thank you, Peter. That was a great point. Yeah, I had the privilege of interviewing Jim last year. That was really an amazing guy. Thank you very
To switch topics, right? That's simulation. There's a couple companies that are in the collaboration workflow PLM space. Tony DeFuso,
Oh, yeah.
who's the CEO of Siemens Software, right? He's on PLM. He's downstairs, right? So you get out and network. There are people who really can influence the trajectory of your companies.
And so yeah, take advantage of tonight after Collab to go downstairs in the partner event. All those guys will be down there. Peter and I can introduce you to them because we both, obviously Peter knows more than me. Thank you very much.